Hello everyone, this video will talk about a buffer solution which is in action. Okay, so what do we mean by that? Okay, so then let's start read the question. Okay, so the question is talking about we have a buffer. Okay, then of course definitely sometimes we could simply say we have a solution. Then you should be able to recognize what that solution is. Okay, so then let's see. The question is telling us, of course, it already said it was buffer, but just pretend we didn't see that. And then if we just say, okay, we have a solution, okay, then let's see what we have. Okay, so this HC7H5O2 I don't know what it is. Okay, but however, we see an ionizable H. Okay, so which means this acid. Okay, so and then what kind of acid? Since it's not one of our strong, so then that's a weak acid. Okay, so you have a weak acid, and then what's this? You go, oh, that's a salt. Okay, itself is a salt, but then we also know how salt behave, right? Okay, so when salt in aqueous solution, 100% dissociate into ions. So we have lithium ion and C7H5O2 minus, these two ions, okay? And then since we're also concerned about pH of the solution, so lithium ion itself is the counter ion of a strong base, so it's pH neutral. So if it's pH neutral, so we don't need to concern about it. So the active ingredient is C7H5O2 minus. Okay, so then I see, okay, that and HC7H5O2. What's the relationship between this weak acid and this anion? Then you recognize, okay, so they're the conjugate acid and base pairs, which means this is weak acid and this is its conjugate base. So then we know this is the definition for buffer. So we actually have a buffer. Okay, so again, either way, we tell you upfront, or if we didn't, then you should be able to recognize it. Okay, so then that's a weak acid and conjugate base giving us a buffer. So we have a buffer. So let's start to draw that. Okay, so just say I have a beaker. Inside this beaker, I have this buffer. Okay, so inside this buffer, I have this weak acid with its conjugate base. Okay, so then let's see what happens now. Okay, of course, we could calculate pH of this buffer, but that's what now this question is concerned about. Let's see, the question is concerned about what's the pH of the solution after addition of 100 ml or 0.1 molar of HCl. Okay, so now the question is, right, this scenario is we are adding, okay, some HCl into this buffer. HCl is a strong acid. Okay, so we're adding some strong acid into this buffer. Then the question, this is what we call it as buffer in action. Okay, so then you have to know how buffer, right? What does buffer do? Okay, how does buffer work? Okay, so as we also learned, right, the buffer system will resist changing in pH, and this how we could reflect that by setting up a reaction. Okay, so in terms of that, since you were adding some acid, if the solution wants to resist changes in pH, which means the acid needs to be neutralized. By whom? Okay, from your buffer, who can neutralize the acid? Think about it. We have weak acid and its conjugate base, right? Yeah, the base sounds about right. If we're adding some acid, the base will come neutralize it. Okay, so they will react. Okay, so then if you feel comfortable, you can just use what we had, right? Okay, so in terms of you can keep the whole salt or just the anion. Either way is okay. So this salt is gonna react with this added acid, giving us H, right? Neutralize it, right? Okay, so giving us the weak acid and lithium chloride. Okay, so then this is the reaction. Okay, so then again, since we're tracking how the reaction goes, we have certain amount of each. So then we need to do a stoichiometry calculation. Okay, in order to do a stoichiometry calculation, we need to use moles to track. Always start with the inventory, how it's reacted according to the stoichiometry, and then after the reaction, what do we have? Okay, so then that's what we're gonna track. Okay, so moles of this, right? We start off with as 0.250, but that's molarity. But then you go, oh, that's not a big deal. I have volume. So with molarity and volume, definitely I can calculate moles. So I'm gonna do one of the calculations. Since numerically the value is quite straightforward, so I'm gonna show you one, then you see how the other is done. Okay, so 0.50 is mole per liter. Then you recognize if we multiply the volume, also cancels out. So that's 0.250 moles. Okay, so then that's the value we want to use. So let's start with 0.250 moles. And then since volume is 1 numerically, right, that's very easy. So the amount of this HCl added is what? Is 100, right? 100 times 1 converted to liter. You could do that work. Okay, yeah, we'll do it. Okay, so moles of the HCl, we'll be able to do it as 1 molar is mole times liter, 100 ml, but this 100 ml could be easily converted to liter. Okay, so that cancels out. Then we'll be able to calculate this. Turn out to be 0.1 moles of this added acid. Okay, so then that also makes sense. You are adding small amount of this strong acid into your buffer, then your buffer going to neutralize it and resisting the changes in pH, and therefore this added acid, right, most cases it should be our what, the limiting reagent. So then that's going to be all reacted, right? Okay, so then it's all gone. Of course, just numerically from math wise, you also can tell the same story. Okay, and then the question will be, okay, what do I have over here? Okay, we didn't talk about that yet. Okay, so then let's talk about that. How much of this weak acid we start off with? Remember, we started with as a buffer, there is, right, there's some amount. How much? That 0.50 in 1 liter. Of course, we can do the same calculation as previously. So then this is also 0.150 moles. In terms of, you can use 0.50 times 1 liter, giving you 0.150, right? Okay, so then that's very, very important for you to recognize and keep in mind. We start off with a buffer, so of course initially you have certain amount of that weak acid right over here and with this conjugate base. Okay, so there are values starting off. Okay, and as we already mentioned, since HCl, the added strong acid, is your limiting reagent, so then also the reaction goes by 1-to-1 ratio. So then you're going to use 0.1 moles of that conjugate base to neutralize it, and then producing 0.1 moles of that weak acid, okay, during this process. Okay, so after the reaction is done, we'll be able to get this value is 0.150 moles of this conjugate base. Okay, and this will be all gone as already analyzed, so it's all gone. And whilst we will be in total, after reaction happens, we have 0.250 moles of this the weak acid. Okay, so then you realize, okay, after the reaction, okay, so after the reaction, I have that many moles of that conjugate base, that many moles of that weak acid. You go weak acid with its conjugate base. Oh, I still remember what that is. We call that as our buffer. Okay, so sometimes I like to call it as a new buffer since quantity wise it's changed, but no matter what, we're happy with this scenario because once we know I have buffer, Henderson-Hasselbalch equation can be used to do the calculation. So pKa of log using the concentration of base over the concentration of acid. Okay, so then pKa, since K is given, that's easy, negative log of that value. So negative log of this 6.5 times 10 to the power negative 5 plus log. Again, you go, oh, I'm calculating concentration. We're getting moles at this point. So let me calculate concentration by dividing volume. That's good. Okay, but you also recognize since we're doing concentration, a division between the concentration. And then since concentration is what? Concentration, let's do one. Right? Concentration of base should be moles of the base divided by the total volume, right? Okay, so since the buffer is in the same solution, so the volume will be the same. So numerically, when you do the division, right? Okay, so then it's gonna be moles of the acid divided by the total volume. Since they're in the same solution, this volume is will be the same value. So the product of the division between the concentration or equals to the division or the product of the mole ratio. Okay, so therefore in this case, when you use Henderson-Hasselbalch, right, the mole ratio equals to the concentration ratio. So if you oh, this is easy, so then we can just directly use that mole information. Okay, so then the next question will be, which one is the base? Right, there's something we also should be able to recognize. Look, that's your base, right? That's the active ingredient, that's the base part. Okay, so then the base goes on top, so that's 0.50, and then the acid itself will be 0.250. Okay, so now do the division, take a log of that, and then calculate what's the negative log of 6.5 times 10 to the power negative 5. Now be able to calculate pH of this buffer after you added some little amount of strong acid. Okay, so then that's the answer, 3.97. That's the pH of this buffer after you added some strong acid. Okay, and then again, that's you, right? Once adding the strong acid, this is the equation needs to set up. Of course, when it's adding a strong base, right, the initial equation will be different, okay, because in that case, when you added some strong base, the weak acid is going to come neutralize it. But as long as you understand how the reaction goes and why it happens that way, then you will always be able to figure this out. Okay, so then this is about pH of a buffer with added strong acid, and hopefully this is helpful, and thank you for listening.